I've got Wozniak, the ROM monitor code from the original Apple I computer written by Steve Wozniak, running on my 6502 breadboard computer. And I've got a previous video that talks about what it can do. But a number of people are interested in more details about how it works. And so here's a copy of the original instruction manual that came with the Apple I. And it includes the code for Wozniak. So that's where we'll start. I've got that original code typed in here. And you can see there's some identifier names like, display, keyboard control register, display control register. And these refer to addresses in memory, either for variables or hardware I/O. So if we look here, you can see there's a list of variables that they've got here. So the page 0 variables are stored in memory at the beginning. So 24 refers to memory address 0024. But defining it as just 24 has a couple advantages. So these variables are replaced in the code when it's assembled. So for example, here we've got store Y display, DSP, and that gets assembled into the opcode for store Y, or 8C, and then the address for display, which is D012. It's in a different order there, but that's how it assembles. And so D012 is just the address for display. So that gets assembled into 3 bytes, that one instruction. And that has to be that way because the display is hardware mapped to that address. But if you just want to store a value in memory, you can use a page 0 variable, or a page 0 address, which is just 1 byte for the store instruction and then 1 byte for the address. So for example, here, we have store x h. So h is the variable. So store x is 86, and then h is just 29, right? So 29 is the h variable. And so that makes your program smaller. And remember, all of Wozniak is crammed into just 248 bytes of code. So that's kind of a big deal. But it also makes it faster by 1 instruction cycle. So, in general on the 6502, you want to have your most used variables in page 0 like this. And so I've got all those variables defined up here like this, and these are just substituted when the program's assembled for these numbers. And then all of the code is meant to be in ROM at address FF00. So I'll define the start here at FF00 like that. Now, when the 6502 is reset, it starts executing at whatever address is in the reset vector at FFFC. And so in this case, at FFFC, now these bytes are in opposite order again, but it's FF00 is where it starts executing. And so that's the beginning of the code here, this reset. And in fact, this first section here is only run when the computer is reset. And it basically just sets up the display and keyboard, loading a value into the Y register, writing it to the display, loading a value in the A register, and writing it to the keyboard and display control registers to get the hardware set up. Now, we don't have the same display and keyboard, so we'll need to change all of the setup code to get it to work on my computer. But after the setup code, this next section is the code that lets the user input a command. Now, it's a little bit funky how we get into this, but I think to understand it, let's start down here where it's waiting for a key press. So right here, we'll talk about later how we get here, but right here, it's checking the keyboard control register and then branch if positive back to next care. So it just sits in a loop here until bit 7 of the keyboard control register flips, which indicates that a key was pressed. And then if a key was pressed, it drops down to here where the key is loaded into the A register. So once we've got a new key press in the A register, it gets added to a text buffer that contains everything that the user has typed so far. So the key press is stored at in plus Y. And in is, address 0200. And then the Y register is an offset. So for example, if we type ff00.ff0f, until you hit enter, it's putting each of these characters into memory at 0200, 0201, 0202, and so on. And then when we hit enter, that's when it'll figure out what to do. And you can see here, in is 0200, but really it has this whole range allocated for the input buffer. So for now, it's just storing each character in memory at address 0200 plus this offset Y, which you'll see get incremented after each character. Then it jumps to a subroutine echo, which will echo the character back to the user so you can see what you're typing. And then it checks to see if the key you hit was enter or carriage return. And if not, it loops back to the top up here. And something to note is that on the Apple I, all of the characters coming from the keyboard had bit 7 set. So this 8D is kind of a strange representation for carriage return. If you look at a normal ASCII table, carriage return would be 0D, but here it has to check for 8D because that bit 7 is always set. But anyhow, if it's not a carriage return, then it loops all the way back up to the top here, where it's checking to see if you hit a couple special keys. So if you pressed backspace, then it'll jump down here to this backspace routine. If you press the escape key, then it'll jump down here to escape. Otherwise, it increments Y and then jumps down back here to next character where it will read from the keyboard again. So the normal path here is to, read a key, put it in the buffer, echo it, and then jump back up to the top, increment Y, come back down here, read the next key, and so on. But let's say you did hit backspace. So you get up here and you detect, we hit the backspace key, which on the Apple I was a DF. First it'll echo the backspace key, which will move the cursor backwards. It's not carriage return. Comes up here, detects, yes, we hit backspace. Now it'll branch down here to backspace, where it will decrement Y. And so that moves us backwards in our text buffer so that the next character typed will overwrite the previous character typed. But then there's a check here to see if we backspaced beyond the start of the line. And so this is kind of nice. You can see here if I type A, B, C, and then I press backspace, 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 it just drops down to a new line so I can start over. And so that's what this does. If we decrement Y and then it wraps around and becomes negative, branch if minus, then we just jump up here where we load a carriage return, echo, and then load a 1 into the Y register. And the reason it initializes Y to 1 instead of 0 is because right after it does that, we hit the decrement Y for backspace. And then, of course, it's not minus anymore, it's 0, and we're right back here waiting for the next character. Now, if we go back here, if we hit escape, that prints that initial backslash prompt and resets everything. And you can see here how that works. So if we come through here, we've detected an escape, then it branches here to escape. It loads the character for backslash, it echoes it, then a carriage return, and it echoes that, sets Y to 0 by setting it to 1 and decrementing it, and then waits for the first key press. But that leaves an interesting question. We talked about this reset code up here. So when the computer's first reset, it runs this code to initialize the hardware, but then it just falls into this code here. So, what happens? Well, the trick is that the display register for the hardware needs to be set to 7F, and the code uses the Y register to do that. And so then when the reset is finished and we fall down into this code here, the Y register is set to 7F. Also, the A register happens to have A7 in it, so that doesn't match a backspace, it doesn't match escape. But when we get here to increment Y, because Y had a 7F in it, it's now incremented to 80, which has that top bit set, indicating that it's negative. Now, BPL means branch if positive, that is if the top bit isn't set, but since now it is, we drop into this escape routine. And so that prints the backslash, prints the carriage return, initializes Y to 0, before ultimately ending up down here waiting for the first character. Now, if you're a 21st century software developer, you're probably a bit uncomfortable with all the weird dependencies in here. Like initializing Y to 1 instead of 0, and then depending on the backspace routine of all things to decrement it so it actually ends up as 0. That might feel weird to you. Or relying on this hardware initialization code up here that has nothing to do with reading a character to leave this buffer index, the Y variable, or the Y register, which ends up being the buffer index, set to a particular value that will just happen to wrap around and overflow in a way, and then relying on that to actually initialize it. Leaky abstraction doesn't really begin to describe this. But that's what makes this code so efficient. That's how Wozniak was able to pack so much functionality into just 248 bytes of code. Conversely, if you think modern software has gone downhill and become bloated and inefficient and so on, well, maybe some of it is, but modern software is a lot more complex than this because we demand a lot more from it. If you try to do this level of optimization where you didn't care about abstraction at all on modern software, the interdependencies would create so much complexity that it would be, virtually impossible to reason about. I think it's kind of what makes biological systems difficult to understand. Not only is biology complex, but everything is sort of dependent on everything else in subtle ways, kind of like this in a way. And I don't know, maybe that's the future of software systems, is to use AI to evolve them into something more akin to biological systems. Who knows? Anyway, I'm getting a little bit philosophical here. But anyway, the point is that by the time we get down to here, whatever we typed is in memory at address 0200 through 027F. If we inspect that address, we can see 30, which is ASCII for the 0 character that we typed, 32 is ASCII for the 2 character we typed. Then 0, 0, 2E corresponds to the dot. Then 0, 2, 7, and then 4, 6 corresponds to the F. And then 0D is the carriage return that we entered. So sure enough, what we typed is in memory here. And then this next bit of code goes through that, parses it, and does whatever the command tells it to do. So to parse the line, Y is initialized to 0. Well, it's initialized to FF and then incremented down here where it wraps around to 0. Then the A register and X register are also initialized to 0. Then for now, since A is 0, this arithmetic shift left doesn't do anything to the A register. And so we store A, or 0, into the mode variable. And mode is going to keep track of which type of command we're dealing with. So 00 is examine. So that's the case where we type in a single address to examine what's in it. Then 7B is store. That's where we give an address and a value to store there. So if we look at 0300, now it's got a BE in it because that's what we stored there. And then AE is block examine. And that's where we want to examine a block of addresses. So here we start going through the input character by character. Y starts as 0, so we get the first character from the input buffer. And if we get a carriage return, then we're done. We jump back up to getLine, which is above to get the next command. Next, it compares with a dot. AE is a dot, as the comment indicates. And the way compare works is that if the character is greater than dot, it'll set the carry flag. So this branch carry clear will get taken for any character value that's less than a dot. So a comma or a space, or really any of these characters that are less than dot. So not numbers and letters and that sort of thing. And that just jumps up here to blank skip, which increments Y and moves on to the next character. And that's part of what lets you enter multiple commands like this. If you want to examine 0200, 0201, and 0202, the parser just skips over the commas and spaces and such while just looking for the next command. But if it's equal to the dot that we compared to up here, then that suggests that we're dealing with something like this block examine mode. So here where we did 0200 dot, that dot signifies, hey, we're doing a block examine. And so if we jump up to set mode up here, it stores the dot, which on the Apple I is AE hex. So that's why AE represents block examine in our mode variable. On the other hand, if we encounter a colon, which on the Apple is BA hex, the colon means we want to store this value at that address. So if we encounter a colon, we jump up to set store. And this does something a little bit odd. It does an arithmetic shift left before setting the mode. So instead of the colon, which is, this BA is the colon, instead of just setting that as mode and using, BA for store, this shift turns BA into 7B by, shifting all the bits to the left. And then it just ends up using 7B as the mode for store. Now, why does it do that? We'll get to that in a minute, but the result is that the mode variable gets set just like this comment suggests. So 0 means in exam mode, 7B is for storing, and AE is for block exam mode. And then finally, it checks to see if we got a capital R. And in that case, it will jump to the last address that was examined. And that's what the run code does, which we'll look at later on. But once we're done parsing any of that stuff, if there was any, we end up in this next section of code where it tries to parse a hex value. I'll scroll down here a little bit. And so we're starting out here. The X register will be 0 here. So we're initializing the L and H variables to 0. And then we save the current value of the Y register into this Y save variable. And so remember, the Y register is tracking the index of which character in the input that we're currently parsing. And then L and H are going to end up with the low and high byte of whatever hex value we're about to parse. And so here it grabs the current character that we're parsing, and it's going to convert that character to a hex digit. So to understand what it does, here's an example of a numerical digit, in this case a 3, and a hex letter digit. I guess it's a hexit, not a digit, but whatever. B. And on the Apple I, the keyboard gives you ASCII with the top bit set. So 3 is hex B3 is the Apple I's version of ASCII for that. And then a B is hex C2. And there's the binary for each of those. And I guess something else to note is that WASMON only works with capital letters. So as you'll see, this code kind of depends on this being a capital B. But in either of these cases, the first thing that the code does is XOR with B0 hex. So here's B0. And for the number, that just flips all of these first bits to zeros. So you end up, we started with a 3 character, and now we just have a 3. So you can see in the code, here's the XOR B0, and then it checks to see if it's less than 0A. So in other words, 0 through 9. If so, we jump down here to digit. Otherwise, we do some other stuff. And so the other stuff applies just if we have something that's not a digit. And the first thing we do is add with carry 88. And because we just did this test, the carry bit's always going to be set in this case. So really we're adding 89 is what that ultimately ends up being. And that gives us this, if we just add those, which is FB in hex. And so what this process does is effectively map the characters A through F into the hex FA through FF. So we started with a B and we end up with FB. So here's the code. We do the add with carry 88, and then it compares to see if it's less than FA. So if it was a digit 0 through 9, then we're already down here in this digit code here. But now if it's less than FA, then that means it's not FA, FB, FC through FF. So that means that the character is not 0 through 9 and it's not A through F. So we've got a non-hex character. So that could be a carriage return or who knows, but we're done parsing the hex number, and so we jump down to not hex, which we'll get to in a minute. Otherwise, we do 4 arithmetic shift lefts. And what that does is it shifts the 4 bits of the digit over to the left. So if we typed a 3, we now have 30. If we typed a B, we now have B0. Next, we'll want to shift that into the H and L bytes in memory, where we'll be accumulating the 16-bit hex number that's being typed. And so the way that'll work is, let's say we typed a B like this. So after this whole process, we'll have B0 in the A register, which in binary looks like this. And basically what we want to do is shift those 4 bits into L, or the low byte here. So what we can do is we can do an arithmetic shift left on the A register, which will shift all of this to the left. And then this bit will fall out and go into the carry flag. And then we can do a rotate left of L. And rotate left is a little bit different than shift left, because when we rotate left, when we shift left, a 0 would come into this empty bit over here on the right. But when we rotate left, whatever's in the carry flag gets rotated into the right here, and then whatever came out the left, this 0 in this case, goes into the carry flag. So we shifted this left to get that 1 into the carry flag, and then we rotated this left to get that 1 into the L, or low byte variable. Then we could do the same thing. We can rotate left H, and that'll put this 0 that came out of the left of the low byte into the right side of the high byte, like that. And so that shift left, rotate left has the effect of just moving all of this to the left by 1 bit. We could just do that 4 times, and then the result will be that after typing that B, the 16-bit value represented by H and L is going to be equal to B. Then if we were to type a 3, for example, we'd have 30 in the A register, and we shift that in, the B would move over, and this 16-bit value would be 00B3. If we then typed an E, we would have 0B3E, and so on. So back to the code. Here's the arithmetic shift left for the A register, then rotate left L, rotate left H, and all of this is in a loop where X is initialized to 4, and we decrement X each time and branch back up to hex shift here, so that it goes through this loop 4 times until X gets to 0, and then it drops out. And so once it shifts those 4 bits, it increments Y to move to the next key that was typed, and loops back up to process the next hex digit. And something else of note here is that this loop is using branch not equal, which will branch up to next hex, which is just up here. It's the beginning of where we parse the next hex digit. But branch not equal will branch as long as the result of this increment of Y is not 0. But Y is never going to be 0 here because we just incremented it. So, as the comment suggests over here, this branch is always taken. So why not just say jump next hex? Well, it's another optimization. So the jump instruction takes 3 bytes. So it would be 1 byte for the jump opcode, and then 2 bytes for the address that it's jumping to. But a conditional branch like this branch not equal uses a relative address. And so the assembler is going to actually replace this next hex, not with the actual 2-byte address of this instruction, of this load A instruction, but it'll replace it with an offset, either a negative offset to go backwards or a positive offset to go forwards. And it'll use just 8 bits to set that offset. So one limitation of conditional branches like this is that you can't jump more than 127-ish bytes in either direction. But here it's not jumping very far. And so Wozniak was able to save a byte. Although again, at the creating a subtle unrelated dependency here on this increment instruction and the state of y. But because this branch will always be taken, it'll keep parsing hex characters and shifting them into the H and L variables until it encounters a non-hex character of some sort. And the result of that is that we can type one hex character, just like 1, and hit enter, and it interprets that as 0001 because it just shifted that 1 in on the right side here. If I type 12, well, then it interprets that as 0012. 123, it interprets as 0123. Obviously 1, 2, 3, 4, it'll interpret as 4 digits. But if I do 5, 6, 7, these first digits just get shifted out, and I'm left with the last 4 so it interprets 1, 2, 3, 4, 5, 6, 7 as address 4, 5, 6, 7. So it's just going to parse hex digits until it runs into something that's not a hex digit, like a carriage return or something, and it catches that here and continues on down here at not hex. Here, the first thing it does is it compares the Y register to the Y save variable. So it's comparing to see if Y is the same as what it was before we started parsing any hex digits, right? Because we stored Y into Y save up here before we started parsing hex digits. So if we come down here, and it turns out that Y is still equal to that same value, well, that means we didn't actually read any hex digits at all. And so that's not a valid entry. And so what it does is it just jumps up to escape, which just resets everything. So that handles this case here where let's say we want to examine 0200 through blah, which is not a valid hex entry. So what does it do with that not valid hex entry? Well, it has the 0200, so it was able to print that much. But then when it gets to this, it's just like, I don't know what to do with that. So it just goes to escape, it prints the / prompt, and just resets everything. So all of this functionality in just 248 bytes of code, and it still does a pretty reasonable job of error checking. But if we make it past that, we must have gotten at least some valid hex characters, so we have some sort of address that we're working with. And here's where it needs to decide what to do based on the mode variable. And the way it does that is pretty interesting. It does this bit test on the mode variable. And to understand the effect of that, let's go back and look at the different values we had for mode. If we go back up, examine mode is 00, store mode is 7b, and block examine mode is AE. And remember, it was kind of weird that the mode value came from, the value of dot or colon read from the keyboard. But for store, we did the shift left, which gave us 7b, and that seemed kind of strange. But if we look at the binary representation of those 3 values, they happen to have the top 2 bits set in a very particular way. So this bit here, bit 6, is a 0 for examine and block examine, and a 1 for store. So that bit there you can think of as indicating whether we're examining or storing. And then if we're examining, this bit 7 is either 0 or 1 to indicate whether we're examining a block or just examining a single byte. And the significance of this is that one of the things that the bit instruction does is it sets the overflow flag based on bit 6, and it sets the minus flag based on bit 7. So just by doing bit mode, these 2 bits get put into CPU flags that we could use for branching. So we do bit mode to set the flags, and then branch if overflow is clear to not store. Because if the overflow flag is clear or 0, that means we're not storing. And if the overflow flag is set, or 1, then that does mean we're storing. So I think this comment is actually wrong, because if bit 6 is set, then we're storing. If it's clear, if it's 0, then we're examining or block examining, right? Because it's saying if it's clear, then we're not storing. So I think this comment is actually wrong. In fact, even the printed Apple I manual says bit 6 equals 0 for store. But that's not true. Bit 6 is going to be 1 for store mode. And, I kind of looked, I was surprised I couldn't find anyone else that, pointed out that this comment was wrong. And, surely I'm not the first person to notice this. But anyhow, if we're examining, overflow will be clear and we'll branch down here to not store. And here the branch if minus will jump if we're doing a block examine. This comment is correct. But just to examine a single byte, it'll drop through to here. So this block of code copies the hex address that was entered from the H and L variables, and it puts it into the store L and store H variables and the exam L and exam H variables. And it does that with this sort of weird loop thing, which again is there to save a few bytes. X starts as 2, and then it loads L minus 1, comma X, so actually plus X. So it's L minus 1 plus 2, if X is 2. So this is actually L plus 1. And if you look, L was in address location 28, L plus 1 is 29, and so that's actually referring to H because of the way these are organized in memory. So the first time through this loop, this is actually going to load H. And then using the same logic, it's going to store it in STH, or store H. And it's also going to store it in exam H. Then it decrements X, and X is now going to be 1, so it's not 0. So we jump back up here. And now when we're loading L minus 1 plus X, X is now 1, so it's L minus 1 plus 1. So now we're loading L, storing it in STL and exam L. And then we hit this decrement X again, which decrements X to 0, and then we fall through this branch and continue on. So that has the effect of copying whatever is in H and L to STH and STL, as well as exam H and exam L. I'll show you how those are used here in a minute. But after we fall through this branch not equal, we're also going to fall through this branch not equal and end up here where it's going to print out the address. So we load this is the character for a carriage return, and we jump to echo, which will just print that carriage return. Then we load the exam H, so the high order byte. We jump to a subroutine that'll print the byte. We load the exam low, the low order byte, and we print that byte. Then we load this is a colon, and we print that out. And we load a space, just a blank, print that out, and then finally load the actual data using an indirect read and print that byte out. So all of that's just doing this print that we see, where it prints a carriage return, and then the high byte, the low byte, a colon, a space, and then finally the value. So that's pretty straightforward. Then the mode is reset to 0. So the X is still 0 from this stuff up here. So it stores X into mode, so it resets the mode to 0. And that's so that if we do something like this, where we look at, say 0200 through 0205, it'll reset it to just regular examine mode. So we can just do space 0300, and it'll print that range 0200 through 0205, and then it defaults back to just regular examine mode where it just prints a single value 0300. So it resets mode to 0 there. And then, let's go down here a little bit. It compares L and H to exam L and exam H. And this might seem a little strange because we just set exam L and exam H to equal L and H. So why would they be different? But this is going to come into play for block examine mode. If we type in something like 0200.027f, the way this is actually parsed is we start out in examine mode, mode 0, and it starts parsing hex digits. So we parse 0200. And then as soon as it encounters the first non-hex digit here, which is this dot, we end up at not hex, right? Where is not hex? Up here somewhere. We end up at not hex, right? And that's where we're checking the mode. And we're still just in examine mode, so it drops down here and does everything that we just looked at. And so when it gets down here and compares exam L and exam H to L and H, it equals that. So it goes back up to the top and continues parsing. Well, that's when it sees the dot and it switches modes. So now it's switched to block examine mode, and then it goes and it parses this hex address. Well, when it's done parsing this hex address, it sees the carriage return, which I'll type right now. So it parses this hex address, and then it gets to the carriage return. Well, the carriage return is not hex. And we're back up here at not hex, which is right here. And so again, we do that bit test on mode. Mode is not store, so we end up down here at not store. But this time mode is block exam. So this branch minus, we're in block exam, it skips all this stuff here and just goes to exam next. And so it doesn't copy L and H to exam L and exam H. It just jumps down to exam next here. And here's where it resets the mode to 0. But now when we compare exam L and exam H to L and H, exam L and exam H are 0200. L and H now are 027F because that's the last thing that we parsed. So then this drops through and we increment exam L. And then if exam L wraps around to 0, we'll also increment exam H. Otherwise, or either way, we'll drop down here. So this is just kind of a 16-bit increment. Then it's going to do this, it's going to AND exam L with 7 to check if it's a multiple of 8. Because, every 8 bytes that we print, we want to print a carriage return and we want to print the current address again, just so we get this nice format. Then it always goes up to next print. And this branch here is taken if the result of that AND we just did says the address is not a multiple of 8. So in that case, it skips printing the address, just prints a space, and the next byte of data. And this just keeps incrementing exam L right here until exam L gets to equal L and H. And so that's how examine and block examine work. So now let's take a look at storing a value to memory and how that works. So if I type something like 0400 colon BE, I want to store the value BE into address 0400. Well, we're going to start out in examine mode because we always start in examine mode. And so the 0400 is parsed as a hex value until it hits the first non-hex character, which is the colon in this case. At that point, because we're in examine mode, if I execute this, it prints out the address and whatever happens to be in memory at that location, which is AB, before we changed it. Then it continues parsing, it sees the colon, and that's going to cause it to switch modes to store mode. And then it sees the blank, it ignores the blank, and then it starts parsing hex value again into H and L. And then at the end of the hex parsing, it encounters a carriage return, which is not hex. And so we're back up at not hex again. So let's go up here to not hex. But now our mode is going to be store mode. And the hex value we just parsed is BE, right? That's the last hex value we entered. So we got some hex digits, so we're going to bypass this. And then we're going to test the mode. Well, now we're in store mode, so we'll fall through this and start doing this stuff. So L contains the low byte, or in this case, the only byte of the hex data that we typed, in this case, BE. So it loads L, it loads the BE into the A register, and then it stores it at store low, comma X. X is 0, so this is really just storing it at the address pointed to by store L, which in memory is followed by store H. So STL, STH is the address that it's going to store to, or points to the address it's going to store to, and the value it's going to store is in the A register, which it just loaded from L. And this STL, STH was the address that was saved back when we were in examine mode and processing this hex value. So 0400, that's what's in store L and store H. So we're basically writing the BE to 0400. Then it increments store low, and if that wraps to 0, it also increments store high, and then it goes to the next item. And it's still in store mode. So we can actually store multiple values in subsequent memory locations because it's incrementing the store address each time. So if we do 0400 colon 00, 11, 22, 33, 44, 55, and so on, the 0400 is parsed in examine mode, and so it just prints out what was there. But then the colon switches it to store mode, and then each time it encounters a new hex value followed by a not hex value, in this case blank, or at the end a carriage return, it stores each of those into the store H and store L address, which it's incrementing each time. So this does kind of what you'd expect. And so if we examine now 0400 through 0407, let's say, you can see it stored 0, 1, 2, 3, 4, 5 in those locations. And then this is just whatever happened to be there before. And so that's actually pretty much all of the functionality of Wasmon. The only code we really haven't looked at is for printing. So if we go all the way to the bottom of the code, here's the sort of printing code that we haven't looked at yet. There's a subroutine called echo, which just prints whatever byte is in the A register. So you can see here it uses a bit test to check bit 7, and then just branches back to echo in a loop waiting for bit 7 to be cleared, which is, I guess, with the Apple I hardware, tells it that the display is ready for a character. And when it's ready, it just sends the whatever's in the A register to the display. So obviously we would need to change this code to adapt to the serial interface that I've got on my computer. And then once it displays that character, it returns from the subroutine. Then there's another subroutine for printing a hex character of whatever happens to be in the low 4 bits of the A register. And it's pretty straightforward. It zeroes out the high 4 bits by ANDing it with 0F. And then by ORing it with B0, it maps the values 0 through 9 to the digits 0 through 9. And then it compares here. If it's less than 10, basically, then it jumps down to echo and prints out the character 0 through 9, whatever the character was. If it's greater than 10 or greater than equal to 10, then it adds 6 to it. And so that basically just adds an offset so that, BA becomes the appropriate character for the letter A. And once it does that, it just falls through to the echo routine here, which will print, whatever letter A through F. And then this return from subroutine will return from the print hex subroutine in that case. And then finally, there's a subroutine for printing a byte. And what that does is it pushes the A register onto the stack, then shifts it right 4 bits, and then calls the subroutine to print a hex digit. So by shifting it right 4 bits and printing the hex digit, it prints the first character of the byte. And then this subroutine, is the one we just looked at. It returns and comes back up here. And we pull A off the stack. And so we end up with A where it started. And then this AND here, we fall into the print hex. And so now it prints the second character of the byte by, falling through here and falling into echo and printing that character. And now this return from subroutine actually returns from whatever called print byte. So it's kind of clever how all this works together and falls through. So you have one return statement here for 3 different functions that all do sort of different things. I think that's kind of clever. But anyhow, that's a complete walkthrough of how Wasmon works. I hope you found that interesting. And, as always, thanks to my patrons for making this kind of video possible. This is definitely not the sort of content that's going to win YouTube. But I like that I can do these deep dives and, a few people are interested enough to support this sort of thing. So thank you.